Thanks everyone for coming to this talk. So this is going to be a talk about Q star, separation logic, and F star by primarily really by Kesha, Hietala, and Nick Swamy and Sarah Marshall. Kesha and Sarah couldn't make it to Slovenia. Nick had the clever idea of becoming the chair of ICFP 2023. So the conference will come to him next year, so he doesn't have to come here. So I'm here and I'll be presenting this work. But again, the credit goes to my collaborators. So I'm going to be talking about quantum separation logic a bit. So first, let's talk a little bit about separation logic itself. So separation logic is an extension of Hoare logic with additional operators. And sort of the main one is the separating conjunction or star. And the separating conjunction describes disjoint parts of the heap. So if you look at, do I have a pointer here? Yes, if you look at this statement over here, it's saying that X and Y are both 0 and they're distinct. They're not aliases of one another. So the frame rule, which is an important rule in separation logics in general, says that if we can prove something like P, C, Q, and we have some additional predicate that we would like to hold R, we can just sort of add it to the precondition and postcondition as long as nothing in reference by R is being modified by C itself. So this is very natural that we should be able to extend a logic in such a way. In quantum separation logic, the idea is that we're going to use star to describe separability of quantum states. So if we say P1 star P2, what we're saying is we have some global state that we can partition into psi1 tensor psi2 such that psi1 satisfies P1 and psi2 satisfies P2 or vice versa, whatever I was supposed to have said. And this is convenient for describing whether or not states are entangled, and it allows us to reason modularly about parts of the state that are not entangled. So we don't have to consider the entire quantum state when we're doing our reasoning. So that's nice. And there have been several very recent proposals for quantum separation logic. But one thing we noticed is that actually there's no implementation for any of these. And when you implement these kinds of things, as Dominic pointed out in his keynote, you really tend to learn a lot, and often you're going to revise the thing, or you're going to just get a tool that's really useful. So that was our thought was, what if we tried to do an implementation? And in particular, we thought, so we heard of this language called F star, and if you replace we with Nick Swamy, then heard of, we mean built and developed over the course of years. This is a really neat both programming language and proof assistant, and being used for a wide variety of projects at Microsoft Research. And one nice thing about it is that in the back end, it's using the Z3 solver to automate a lot of proving. So that seemed like it might be helpful. And moreover, there's this thing called Steal, which is a concurrent separation logic, so even more than we really needed, that is recently being used a lot in F star because it's really convenient for reasoning about programs in a sort of modular way. So using Steal, we can get a sort of a Hoare logic and a star sort of for free. So that was nice. So in order to interpret star, though, in Steal's logic, we're going to need a PCM, or a partial commutative monoid. And sort of our issue here is that we would like tensor to be the operation here, and tensor is annoyingly non-commutative, even though it's nice to think of tensor as being something that is commutative. If you think about the concrete Kronecker product, it really does care about the order of the things that you are tensoring together. So we built off QuantumLib, which is a Coq library we've been using for a bunch of other projects, and ported it over to F star. And then we did still need a commutative version of tensor. So basically we just said tensor plus some kind of swap operator that will maintain that qubits are always in a given order. And that kind of is a slightly hacky way of dealing with this problem. I think a lot of people have been thinking about more sort of principled ways of dealing with it, but it works at least to some extent. So we're going to introduce a predicate, q bar points to psi, that says that the set of qubits in Q are collectively in that state. And implicit here is that they're not entangled with the rest of the system. So we're going to add 4 quantum actions to F star. Allocate, which allocates a new qubit in the 0 state. Discard, which is going to remove a single qubit, leaving a empty predicate, so essentially no information. A measurement operator, so here we have a Q that is entangled potentially with a bunch of other qubits. And we're going to measure Q and assign the output to B. So one thing we're going to get obviously is that Q is now going to point to some to the same value that is in B if we treat B as a quantum state. But we're also going to have to update the rest of the state. And we're going to update the rest of the state by projecting Q onto B in the remainder of the system and sort of removing Q from that system. And then there's apply, which is exactly what you would expect apply to be. And we added an entailment rule, which says that if Q1 and Q2 can be represented as this tensor, then we can split it using the separating conjunction. So here's an example of quantum teleportation, which for some reason is written, that I'll get to in a little bit. We've written in the Microsoft's Q# language. There's probably, you can kind of guess. And let's just run through this example. So it's pretty much your standard teleportation, and you actually just saw teleportation 2 slides ago, or 2 talks ago, so not much to say. But we have our arguments there. We have a return type. We have this nice thing that says is adj, which we'll use almost immediately, which says we can automatically compute the adjoint. So here we're going to use the adjoint because that's a nice part of the encoding part of teleportation. Going to measure 2 qubits, return Boolean values, which we'll use in decoding our message. And all of that comes together in teleport, where we both allocate a qubit for Alice and implicitly deallocate our qubits at the end of this computation. So we have a few things that we want to prove about teleportation. So here are sort of dilemmas you would need. You would prove something about entangled. That's simply that if you give it zeros, it produces a belt pair. Prove something about send message, which is going to be a little bit more complex. But not that much more complex. It says that M and A are going to, at the end of this, let me point this out now. So one key distinction between what we're verifying here and what you saw 2 talks ago is that we're looking at a potentially large state. So there is no guarantee here, as there was in the twist talk, that the message that we want to send is unentangled with the broader system. And that's good, because it shouldn't be, right? Because the whole idea of teleportation is that we want to be able to teleport a qubit together with everything that it is entangled with to this new qubit. And this is often going to be used in practice if we want to do some sort of distributed quantum computing. So here in decode message and in teleport itself, we're going to say B and Q point to phi. Then we're going to have at the end of this, QB and Q are going to point to this slightly different version of phi. And then, so the total teleport here then will take this initial message qubit and whatever it's entangled with are in some state, and some qubit B that's 0. And in the end, B will have replaced essentially the message qubit in this same exact quantum state. So let's take a look at an example. This seems like it should be at the end, but this isn't quite the end. Sorry. So here's the type for teleport, and here's some interesting things. So there's some QSs that could be other qubits in the environment. There's a message qubit, and we specify here it's got to be disjoint from the rest of the qubits. There's the initial state of QM and QS, and there's also Bob's qubit, which is distinct from QNS. Unit return type, and exactly the pre and post conditions that I showed you on the previous slide. So what's the actual term for teleport? It's not as hideous as you might think, especially if I were to show you by comparison the term for teleport in like proved in Coq. So we've got our code. It's just 6 lines of code there. And we've got 2 proof components. One of them is really trivial, and it's kind of annoying that Z3 didn't just discard these, because we just allocated a qubit and we should immediately know that that qubit is not entangled with the rest of the system. Hopefully that's a thing we can automate away so we don't have to say it anymore. And there is a small lemma about teleportation that we have to prove, because there is a little bit of math going on, and that's not something that's going to be automatic. So there's some additional applications I just want to briefly jump over. So that's something that we had to do, at least some manual stuff for. But there's a lot of nice things that F-star should be able to get almost for free, such as discard the safety. That is, that something is unentangled when deallocated. Somebody, I forget whose talk, manages to do this pretty automatically as well. Qubit resetting and reuse to confirm that a qubit is in the 0 state on discard. And no cloning. Let's make sure that qubits are not aliasing one another. And then being passed, for instance, the same function, which would be dangerous. And there's a lot more in Kesha Hietala's thesis. So this is actually building, she originally did this in just pure Q star, that is sort of F star without the separation logic. And that all worked. And then we were like, oh, but if we did it in separation logic, it would be easier and look cooler. So we did that. So there's a few future directions for this. One is we didn't actually take advantage of the concurrency. And it seems like nobody really has thought about verifying some sort of concurrent hybrid quantum classical algorithms. So the infrastructure is there if anyone wants to take advantage of it. There's some rough edges in the implementation and admits in the implementation that we want to fix up. And sort of the last bit, and me giving away the title that was probably fairly obvious, is that we would like to integrate Q star, given that we seem to be using entirely Microsoft products here, into the Q sharp tool chain. So basically, we can translate at least a significant subset of Q sharp into Q star. It would be great to then prove properties of those programs before we go ahead and put it into the new, shiny new intermediate representation that Microsoft and its collaborators have been working on, called rather uninspiringly QIR, for quantum intermediate representation. And I think that's all I've got. Code is available online, and the separation logic is also online. Note that it's in a branch, because there's the main branch is still the old version that doesn't use separation logic, which is also interesting. And yeah, that's all. I'm happy to take questions.
I want to ask a question. I'm going to abuse my position as chair. So what do you get back when the proof fails? What error message can you get, and how useful is it?
I guess it depends on the... Oh, I should use this. So I guess it depends on, how things failed exactly. So it will typically be a Z3 error, and often they are not very helpful if it's just a Z3 error. It will say Z3 was unable to solve this. And that's not great. What I found the right thing to do is, if you get that kind of error, is to try to show something that's sort of intermediate between the thing you wanted and the thing you need, and see if it fails on one side or the other side of that. And then sometimes that will actually just solve the problem, because it will be like it can step from A to B and from B to C, and it just can't make the leap from A to C. But I don't think in general you get great error messages out of this tool, out of Z3 in general.
Yeah, my question is whether, so said you have these different rules for alloc and so on. So is this just axiomatized, or is there a semantic definition of these predicates and so on?
They're semantically defined in terms of the quantum lib. So alloc is indeed allocating a single qubit in the 0 state. So we can say that it's going to be a 0 qubit.
And then you can prove that these rules hold in
Yes.
Q star. Okay.
So, there's nothing, I don't think there's anything axiomatized except insofar as there are a lot of things that are admitted, which is really, just axiom. But, we say that we're going to do it one day.